Section 6.5 is going to look at the central limit theorem. So for the central limit theorem, we're going to look at a little bit of a demonstration first. Normally, if we were in the classroom, we would make a sampling distribution using pennies. We would take many different sizes of samples of those pennies and find the average for the years of those pennies. We would take different sized samples of 5 and 10. It would take a couple of days. But since we don't have that ability right now, we're just going to look at a demonstration that is similar to what we would have created in class. We're going to start off, we're going to look at this population here that is normally distributed. And if I was to take a sample of size 2, here's my sample of size 2, and take the mean of that, then graph it down below. So I'm taking multiple samples of size 2 here. We want to know what will the averages look like if I do this for lots and lots of samples. So if I continue, now I'm going to go groups of 5 and then up it to 10,000 and 100,000 samples at a time. And as you notice, the distribution of our sample means is also normal. The mean is also the same, or approximately the same. Here the mean is 15.99, here it is 16.0, but the mean is still almost exactly the same. This makes sense because the probability of getting some very small numbers or some very large numbers from our parent population is very small. And therefore, the distribution is going to be roughly the same, but because we can not often get very many samples of 2 items on the lower end or 2 items on the upper end, notice that the variation or our standard deviation gets smaller. Let's do another one. This time we are going to take samples of size 5. If we continue to take lots and lots of samples of size 5, notice again that our distribution became normal. And if we do the same thing for a sample size of 10, remember every single sample that we're taking, we're finding all of those values and averaging them to get our one value for our distribution of our means. Again, it became normally distributed. However, look, our standard deviation is getting smaller and smaller. So it was 5 when we have our parent population, and now it has a standard deviation of 1.58. We could do this one more time with a sample of size 25. So theirs was 1, and now we're going to speed it up. And as you see, the mean of our sample here is the same as the mean of our population, but our standard deviation got even smaller. So this is in your notes on the very first part, and those 3 situations, n is equal to 5, n is equal to 10, and n is equal to 25. You have your population at the top, and then this is the distribution of the means down on the bottom. As the sample size changes, how do the means seem? Well, the means seem approximately normal. the mean of our sample means, or the sampling distribution, is the same as the population mean. Or in other words, the mean of all of these samples that we took the mean of is equal to the mean of our parent population. What happens to the variance? We don't focus much on variance in here. We focus more on standard deviation. So what happens to the standard deviation as n increases? Remember, standard deviation is how spread out our data is. So as you notice here, our data was slightly spread. It gets less and even less spread. Our standard deviation was at 2.24 here, 1.58, and then 1.00. We can say the standard deviation decreases as n increases. As our sample size is getting larger and larger, our standard deviation is getting smaller and smaller. And that comes from the fact that we're going to have few samples. For example, if n is 25, we're going to have very few samples where all 25 items are coming from this very low end, and very few samples of 25 where all of the items come from the very high end. You're going to get a mixture which causes them to fall more in the center and be less spread out. The next one that we are going to look at is going to be a uniform distribution. It makes sense that if we have a normal distribution, that the means are going to be normally distributed. But we want to see what's going to happen when we don't have a normal distribution, since a lot of things that we study in statistics are not always going to be normally distributed. This time we're taking samples of size 5 from a uniform distribution. As we take more and more of the samples, notice that we're not getting very many samples in this small end, or means of samples in the small end, and we're not getting very many means of samples in the large end either. And the reason for that being is that notice that we're not getting very many samples in the small end or very many in the large end. And that is because the probability of having everyone be in the low end or everyone be in the high end is very small. When we start taking lots and lots of samples, we see that it appears to be approximately normal. And notice our mean for our sample means is 15.88, and the mean of our population was 15.89. Our standard deviation here for our population was 9.53, and the standard deviation now is 4.26. The data is less spread out, but the means are approximately the same. Now we are going to take samples of size 25. So there's the mean of one sample of 25. And now as we take more samples, we can see that the average or the mean of our distribution is almost exactly the same, or not, it actually is the same as our population. So here our mean is 15.89 and here our mean is 15.89. And we have an approximately normal distribution here. Notice that the variance and the standard deviation is smaller than it was when we had a larger sample, a sample of size 5. So even though we started with a uniform distribution, we still ended up with an approximately normal distribution for the sample means. In our notes, it said to sketch the graph shown. The graph was the parent graph. So a sketch of our parent graph here would look something like this. What kind of distribution does it have? It is uniform. What is the mean and the standard deviation for it? The mean was 15.89 and our standard deviation was 9.53. After the simulation ran, sketch the graph of the distribution of the sample means. We're going to use the second one that we did, the one where our n was 25, or the sample size was 25, and we ended up with a shape that looked something like that. And what type of distribution is this? It is normally distributed. Remember that this is the graph of sample means. So we were taking the mean of a sample of 25 items from our population and then graphing that result. And the mean of the sample means is 15.89, and the standard deviation is 1.91. So does the mean of the sample means target the population mean? Yes, it does. And we saw this because mean is an unbiased estimator. Which we learned in the previous section. Which graph has less variation? The graph of the sample means has less variation. It is not as spread out as the parent population or parent graph. Let's look at one more simulation here. This time we're dealing with a bimodal distribution. We're going to take some samples of size 5. This time we are going to deal with a bimodal distribution, and we're going to take some samples of size 2. We're taking now we're going to look at a bimodal distribution. So this is a distribution where you have lots of data clustered in 2 different locations. When we take samples, we're going to take samples of size 2. You would think, and it makes sense, that we would get a lot of means on the low end and a lot of samples that have 2 items on the high end. And you would think that it would be easier to get some high-end averages and some low-end averages, which seems to be what is taking place right now. However, as we do lots and lots of samples, we are going to see that we don't necessarily get only items on either end. As we take lots of samples, we seem to get this W shaped. Now, if we take samples of size 5, let's see what happens. Our distribution still is kind of wonky and crazy. What happens now if we take samples of size 10? As we take lots of samples of size 10, we're getting something that is closer to a normal distribution. And now if we take samples of size 25, we end up with an approximately normal distribution, where the mean of our sample means is equivalent to the mean of our population. After viewing the different simulations, what conclusions can you make about the shape, the center, and the spread of the sampling distribution of the sample means? The conclusions that we can draw is that the shape will be approximately normal regardless of the shape of the population if the sample size is large. For the first two, our normally distributed population and our uniformly distributed population, we saw that almost all of them, the sample means end up being normally distributed. But when we had that bimodal distribution, the sample means graph was not normally distributed until we had a population of sample size 25, or excuse me, not a population, until we had a sample size of 25. So if the sample size is large, we're going to say bigger than 30. The center remains equal to the population, and the spread gets smaller as n increases. So as our sample size goes up, our spread of our means gets smaller and smaller. Here's some notation for our sampling distribution of our means. If all possible random samples of size n are selected from a population with a mean of mu and a standard deviation sigma, the mean of the sample means is going to be denoted mu of x bar. And it's going to be equal to the mean of our population. This is the mean of the sample means, and it's equal to the mean of the population. Also, the standard deviation of the sample means is going to be denoted by sigma sub x bar. And it's going to be equivalent to the standard deviation of our population divided by the square root of n. The reason why we divide by the square root of n is because, as we saw in our simulation, the larger the size sample we take, the less spread out our data is. And we call that the standard error of the mean. And so we need to make that standard deviation of our sample means closer to the standard deviation of our reverse that. Sigma sub x bar is called the standard error of the mean. We saw in our simulation that our standard deviation of our means got smaller and smaller as our sample size got larger. So in order to approximate the standard deviation of the sample means, or to use the standard deviation of our sample, we need to divide by the square root of our sample size so that we know and can make that standard deviation of our population closer to our sample. This is the standard deviation of the sample means. This is our population standard deviation. And n is the sample size. And this is going to allow us to use our normal distribution rules and that standard normal distribution. The big concept here is the central limit theorem. And the central limit theorem says that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. That was what we saw in our demonstration. When selecting a simple random sample of n subjects from a population with a mean of mu and a standard deviation of sigma, it is essential to know these principles. The first one is for a population with any distribution, if n is greater than 30, so the sample size is greater than 30, then the sample means have a distribution that can be approximated by a normal distribution. With a mean that is equal to the population mean and a standard deviation of sigma divided by the square root of n. The second thing says if our sample is less than or equal to 30 and the original population is normally distributed, then the sample means have a normal distribution with a mean of the population mean and standard deviation of sigma divided by the square root of n. And the last one, if n is less than or equal to 30 and the original population is not normally distributed, we cannot do anything yet. So we'll learn what to do if our population is not normally distributed and our sample size is less than or equal to 30. So as a result, when n is sufficiently large, usually n has to be greater than or equal to 30, the central limit theorem tells us that the distribution for the means is approximately normal, even if the distribution of the population is not normal. And the mean for the sampling distribution is going to be the same as the mean for the population. Really, what I should write this is the mean of the sampling distribution is the same as the mean for the population. The standard error of the means distribution is the square root of n times smaller than the population standard deviation. That's why we have to divide by the square root of n. We already talked about what u sub x bar and sigma sub x bar mean. They are the mean and the standard deviation of our sample means. When we are working with a sample, when we are working with an individual value from a normally distributed population, we use z is equal to x minus the mean divided by the standard deviation. That's what we did in section 6.2 and 6.3. Now, when working with a mean from some sample where our sample size is greater than or equal to 30, or the original population is normally distributed, we use z is equal to the sample mean minus the population mean divided by the standard deviation over the square root of n. This section is not changing all that much. The only thing that's really changing is our z-score or z-value is now going to have that standard error built into it. And when you read a problem, it is going to say the sample of a certain size, but everything else is going to essentially remain the same. So the process that we will go through to solve these problems will be similar. We will find our z-value. We will then look at our normal distribution table to find the proportion and use that to answer our questions. That takes example 1.